Okay, next one. I'm going to read it, see if you can figure it out just by me reading it. An oxygen gas sample occupies 5 liters at 27 degrees Celsius and 1.2 atm. It's cooled to 15 degrees Celsius and a pressure of 780 millimeters of mercury. What's the final volume? That's a lot of info in there.
You said it pretty fast.
Yeah, on purpose. All right, so I'll write this one out and then we'll see if you can figure it out. What's the first thing you should do? Change the Celsius. So we have, what is it, 300? Oh, we didn't have to change liters. Here's the ATM, so we're good. Here's another Celsius. What's this one? And, 780 millimeters of mercury. How do I change that? 780 divided by 760. Ooh, I don't know either. I would do it this way, and if you don't get something that I have for an answer, then I would go back and fix it. Okay. And then what's the final volume? So, in this one we have 5 numbers. We have liters, and we're going to look for liters. We have different Kelvin temperatures, and we have different ATMs. So what's constant? Nothing. Everything's changing. Everything's changing, and there's no moles. Remember, ideal has moles? Because ideal has everything, too. It has the pressure, which we have pressure. It has volume, which we have volume. It has temperature, which we have temperature. But this moles is what makes it not an ideal gas law problem, because it doesn't have moles. Okay. So let's do the start and end. We're starting with 5 liters. I'm erasing this. I wrote ginormous anyway. So we have 5 liters and 300 Kelvin and 1.2 ATM. And we are ending with, we don't know the volume, that's what we're going to find, and 288 Kelvin and 1.02 ATMs, which I could see someone easily screwing that up because they're so close. Is anyone confused about where I'm getting the start and end stuff from? People in the past have been confused by that. Okay, now I have 5 numbers. All the other problems I only had 3 numbers. Now I have 5. Which one do I start with? Volume. When in doubt, start with volume. So we have 5 liters. Do I put liters on the bottom? No. Why not? But that's what we did in stoichiometry. Okay, liters is what we're looking for, so we don't want it to cancel. So first, we need to cancel kelvins and we need to cancel ATMs. Which one should I put first? Really? Yeah, this is why I'm here. Really, it doesn't matter because multiplying and dividing, it doesn't matter the order that you do that in. I always do a Boyle's first and then Charles just because that's the way I learned them. So I make this my Boyle's parenthesis, and I make this my Charles parenthesis. And Boyle's deals with what? Pressure and volume. So pressure has to be ATMs. And Charles deals with temperature, so these are going to be Kelvin. Kelvin on top, Kelvin on the bottom, so they cancel. ATM on top, ATM on the bottom, so they cancel. But now, where do my numbers go? Because I have 2 Kelvins, I have 2 ATMs. So I know the ATMs are going to go here, but which one goes where? The bigger one follows the second arrow. So we have, what is our ATM doing? Going from 1.2 to 1.02. So pressure is going down. So volume does what? Goes up, because Boyle's does the opposite. So volume's going up, so the bigger number goes up on the top. Which one's bigger? Then I have Kelvin. My Kelvin is going from 300 to 288. So what's temperature doing? So what should volume do? According to Charles' law, they do the same. So it should also go down. So bigger number is going to go down on the bottom. What's bigger, 300 or 288? Then there's a number on the top, multiply. If there's a number on the bottom, divide. So I would do 5 times 1.2 divided by 1.02 times 288 divided by 300. $5.65. What's my label? Liters. For 1, the question says, what's the volume? Volume is liters. And for 2, all the labels cancel except for the liters. So liters would stay there. Now, here's my question. I said for Boyle's, Charles, and Guy-Lussick's, you could check your answer, because if you said that the second one goes up and the number went up, then you're right. Or if you said the second one goes down and it went down, then you're right. But how do we check a combined? You could do that. That's good. So you could just do the Boyle's part of it and see if your answer went up from 5. And then you could ignore this and just do the Charles part and see if your answer was lower. So let's do that. So do 5 times 1.2 divided by 1.02. I got 5.88. Did it go up? Yeah. Yep. So then ignore this part and just do this parenthesis. 5 times 288 divided by 300. And I got 4.8. Did that go down? Yes. So if both of them did what you said they would do, then likely you have this right. I always think of a combined gas law as like a battle between Boyle and Charles, and to see who wins. So who actually won? We went from 5 to 5.65. So did we go up or down? So who won, Boyle's or Charles? So Boyle's won. I'm kind of a nerd that way. Did that clear it up for you a little? Did my email make more sense now? The email that I sent you about battling it out?
That makes sense, yeah.
Okay.
Well, it kind of made sense in the email, too.
Okay, good. All right. How are these gas laws hitting you between the ears? Do my little arrow things make more sense now on that cheat sheet? Yep. And you understand that they don't, like, Boyle's is not locked into this. Like, here it is doing the opposite. That's just showing you that they have to do the opposite. So you have to actually look at the problem to see what's going on and then make the other one do opposite.